Okay, so we're going to look at now locus of lines, circles and rays, okay, involved in our Argand diagram. So today we're just looking at the basic principle, what makes a line, what makes a circle, what makes a ray, okay, and then on next lesson, we've got 2 more lessons left after today, which will be locus problems, style question, okay, and then there'll be a working lesson to finish off the topic, okay, and we start complex numbers in week 6 for 5 weeks, the rest of the term. Okay, so first thing we're going to look at some lines. Okay, so we need to illustrate all these examples on the following regions on the Argand diagram that will satisfy the following equation. So first one, so -2 is less than or equal to the real part of z, which is less than or equal to 1, and 2 is less than the imaginary part of z, which is less than 4. Any ideas? Well, it's under the heading lines, isn't it? What if I said the real part was equal to 2, -2? No. The real part is equal to 2. Yeah, vertical line, isn't it? Alright, so for our question here, the real part is -2. And so the real part of z is between -2 and 1 inclusive. Alright, so that means we're going to have 2 vertical lines, one at -2 and one at 1. Alright, and 2 is less than the imaginary part of z, which is less than 4. So what are they going to look like? Alright, now the difference is, this is the less than or equal part, this is just the less than. So how do I distinguish between those two lines? Okay, good. So remembering what we've done in the previous course, in the lower courses, so to speak. Oh, whoops. So I've just said that and I've just done one more thing. Okay, dotted line at 2. Okay, so arrowhead, because we've got a line, means to keep going on and on forever. Okay, and now we need to illustrate the following region. Okay, so which region would I need to illustrate to fit those two? Is it a square though? Not quite. Well, this is the distance 3 here, and that's the distance 2. So are you saying this region here? Yeah, it's not a square. But that region there, okay? Because the real part must be between these 2 points, so this whole thing will be shaded here, and then the imaginary part must be between 2 and 4, okay? So I'll be showing that region there, okay? So like what we've been doing in region mathematics, however, we can treat that as assumed knowledge, okay? So it'll be that shaded region in there. Between all 4 lines, really. Okay, so the real part of z will give a vertical line, and the imaginary part of z will give a horizontal line. Okay? Now, second one. So the absolute value of z take away 2i is equal to the absolute value of z take away 2 plus I. Right. So when the coefficients of z are the same, okay, they will represent lines. When they are not the same, and we'll look at an example further on, they will represent a circle. Okay, so the concept is that the absolute value of z take away omega 1 is equal to the absolute value of z take away omega 2, okay, where omega 1 and 2 are the equations of 2 complex numbers, okay, results in a line that is the perpendicular bisector of omega 1 and omega 2. Okay, so note that the coefficient have to be the same. when you do these questions, you need to treat it like this. So z take away 2i, because that is the complex number, that which equals to the absolute value of z take away 2 minus I. That's how you have to treat it in terms to get the points in the right spot. So a couple of ways we can do this. We can do this algebraically. Okay, so we're calculating the modulus really of these two expressions here. So x squared plus our y take away 2i all squared. So we don't need the imaginary part, just the real part, just the coefficient, sorry. Okay, which equals x take away 2 all squared plus y plus 1 all squared. Okay, so we need to treat it as opposite, so really we're going back to what the original question is, okay, to plot the points correctly. Right, so we can expand all that out and tidy it up, and then I'll give us the equation for line. Okay, and the idea is that your x's and y squares will all cancel because the coefficients are the same for that. Right, so I'm going to bring everything of the y's over to the left hand side. Right, plus 4 will cancel. So I'm left with a negative 4x 1 plus 1. Okay, so that gives us the equation of that line that we need. Okay. So what's the alternate way to answer this question? Thinking back to, let's say, mathematics. This is the perpendicular bisector. You could do it that way. What's the way I'm thinking how to do it?
Get one and change another one by 93.
Sorry?
Get one and change the other one by 93.
If it was just mathematics, if you're looking at this question in mathematics, okay, ignoring that there are complex numbers, what would you be doing?
From this point.
Hey?
From this point or from the beginning?
From the beginning. Well, you find the midpoint. It's the perpendicular bisector. So you find the gradient. Okay, you find the perpendicular gradient from that. Okay, and then you find the midpoint, and that gives you your point and your gradient, and then you substitute in your point gradient formula. Okay, that's the alternate way you can do it. Alright, so or, and that's why we write it like that. Okay? Okay, so we find midpoint. Find perpendicular gradient. Substitute in point gradient formula, so y take away y1 is m outside of x take away x1, and we'll get the same equation. Okay, so before we can do that, we need to remember we need to have omega 1, omega 2, and that will represent where the point is on my Argand diagram. So in other words, z take away 2y. So this is a 0 plus 2i, so that'll be that point there. And z take away omega 2, where omega 2 is 2 take away I. Right, so positive 2 take away 1. Okay, so what you're doing is you're finding that midpoint, there, you find the gradient, you get the perpendicular gradient by doing the reciprocal, change the sign, okay, and that's the locus there, that line that goes, the perpendicular bisector of those 2 points, okay. So you can do algebraically, or we can do our mathematics skills to be able to do that. So y equals 2 over 3x, take away a 6. Okay, so I won't go through all that. Morning. We're looking at locus of lines, circles, and rays. Alright, so 2 over 3x, take away a 6. We're going to have something like this. Okay, doesn't have to be overly accurate. Alright, as long as you're representing general means, we'll how what this looks like. Okay, so negative 1 on 6 for the imaginary axis. Alright, and the gradient has a rise of 2 and a run of 3. Okay, which is a perpendicular bisector. Okay, so to summarise there quickly, we're looking at locus, lines, circles and rays. Okay, so if there's the real part of z, okay, will equal vertical lines, okay, at negative 2 and 1. Okay, so 2 vertical lines there for the real, and the imaginary part are going to be horizontal lines at the values given there. Alright, and we've got the inequalities, so remember back to our mathematics, when we've got equal to a component, we have unbroken line. Okay, but when we've got strictly less than or greater than, we have to do the broken lines. Okay, and the region is the bound between those 2 lines. For there. Okay, when you have the absolute value of z take away omega 1 and z take away omega 2, this will result in a line that is a perpendicular bisector of those 2 points. Okay, so we can solve this algebraically, okay, as it is there, or we set it up this way, we plot the point. Okay, here and here, find the midpoint, find the perpendicular gradient, substitute into your point gradient formula using mathematics skills to find that locus. Okay, so that's what it looks like there. Alright, circles. Okay, so the modulus of z is 3. Okay, so what's the modulus again? The radius, okay? So, logically, this will provide a circle. Okay, so the modulus of z equals r is a circle, that's the centre at the origin and radius r. Okay, common sense there. Okay, so z is of course our same as saying the radius of the circle. Okay, and z conjugate multiplied together will also equal r squared. Okay, because remember the rule from the conjugate theorem, this is x squared plus y squared, and of course using our formula for the circle, okay, in previous mathematics or extension, whatever we've done them in, Locus, that's this equation of the circle. Okay, so that's the other form we can have as a circle. Now remember, the modulus of z is r, z times z conjugate is r squared. Okay, so you have to be careful about what the values of the radius is going to be. So, the modulus of z is 3. Okay, so we put a circle there. Okay, using your circle drawing instrument. Okay, and it probably will be a good idea to label it. Do we label the I when we do imaginary? I can't remember. Do we label I when we label the point on the imaginary? Alright, good. Now, the modulus of that equals or is an inequality of a number will also represent a circle. So previously we had the modulus of z take away omega 1 is equal or inequality to the modulus of z take away omega 2. That will represent a line because the coefficients are the same. Okay, but when you've got the modulus of z take away omega 1 is going to be equal to or going to have an inequality of a number, this is also going to represent a circle. Okay, so z take away omega, take the modulus of that, equals r, it's a circle, centre at omega and radius of r. Okay, now this has to be in z take away omega form. Alright, so in other words, you're going to have to factorise. So minus 2 minus 3i, less than or equal to 2. So omega is negative 2, take away 3i. Okay, omega is not 2 plus 3i. Because of the format that we need here, the negative here. So I've taken the negative, then that must be my omega there. Okay, so we've got the centre at negative 2, negative 3i, and radius r. So whatever that value is there, that is the radius. Not radius squared, it is the radius. Okay, so we've got a radius of 2. Okay, of course we've got a radius of 2, that means this part of the circle will be on the axis. Okay, because we've gone negative 2 and negative 3, the radius of 2 must touch back at the imaginary axis. Okay, so I'll be labelling those 2 points, at least to get the centre. Okay, and we can tell from the radius that they're going to have an x-intercept. An imaginary axis intercept, which I have already labelled. Alright, any questions? Right, next one. We've got z take away 2 plus 3i, and the conjugate of z take away 2 take away 3i is equal to 4. Right, these are all in your notes. Alright, I'm just doing a summary here. So everything I do here will be in your notes, okay? I'm just doing a summary so that we can just look at it here rather than going back and forth in your notes. Okay, it's all there. So the format is, so we've got z take away omega, and the conjugate of z take away the conjugate of that same value omega, okay? That will equal r squared. Okay, so the centre at omega and radius r. Okay, so the radius, this one's going to be 2, right, because this is r squared is 4, so r is 2. Right, and again, we need to have the negatives in there. Okay, so you need to be careful about where the centre of that circle is going to be. Okay, so in other words, this is z take away. I would go to the point where you're factorising. So 2 take away 3i. And I've got z conjugate take away 2 plus 3i. Okay, so these two are conjugates. Okay, so the sign between the real and imaginary has changed. So that's what the conjugate is. So I've got centre at omega. Okay, so omega is 2 take away 3i, and the radius will be 2 squared. Oh, what have I forgot to do here?
Define the region.
Yeah, I haven't defined the region because of the inequality. Okay, so it's going to be less than 2. Okay, so that means it's going to be inside the circle. Okay, so if you don't believe that, you can test a point, substitute it back into the complex. Okay, so you put that point in for z. Okay, put that complex point in. So 0, 0, for example. Then prove that the modulus of 2 plus 3i is less than 2. Not sure, you probably do it. Okay, so let's check our trivial point, the origin. Right, so we've got 0 plus 2 and 0 plus 3i. So we need to find the modulus of 2 squared plus 3 squared. I'm sure you got that. And we need to show that that's less than or equal to 2. Right, so 4 plus 9, which is 16, square root of 16. Hang on. 4 plus 9 is 13. So the square root of 13. Is that less than or equal to 2? Alright, so it's not. Alright, so that means the region is without. It's a region that's not including the point of the check. Okay, so in other words, it'll be inside the circle. Okay, and luckily it's less than or equal to, so I've got the unbroken line. Okay, so you've got to be careful about those little things. Okay, just like I wouldn't so much. Alright, so back to this one. Alright, so the centre is at omega, the radius is 2. Alright, so 2 take away 3i. So 2 take away 3i. Somewhere there. Doesn't have to be accurate, alright, overly accurate, as long as it's represented well. Okay. So 2, negative 3. And this one's an equal. Okay, so we just need to do the locus, which is going to be that circle radius 2, centre at omega there. Right, any questions there? F. So the modulus of 4z is equal to the modulus of z plus 2 plus I. Okay, so this is where the coefficients are different. Okay, so we go back to the one that was similar to that one. Here, okay, the coefficient of z was the same. When they're the same, it'll be a line. When it's not the same, it will be a circle. Okay, so the condition is the modulus of az plus omega 1 is equal to the modulus of bz plus omega 2. Alright, we'll also form a circle. So where a is not equal to b, so where a equal to b is a line, where a is not equal to b is going to be a circle. Right, so we have to use an algebraic method to find the centre and the radius. Okay, by doing something similar to what I've already done. Alright, so the modulus said it's going to be 4 root of x squared plus y squared. Okay, so we have modulus there. Okay, this is going to equal okay, so what it is in the brackets is a plus. So we've got x plus 2 all squared plus y plus 1 all squared. Okay, matching your real and imaginary part. Because really what we're doing is finding a distance, so this really should be saying the square root of x plus 2 squared plus the square root of y plus 2 of y plus 1 all squared. Okay, so it's really saying it's just square root. Okay, so what I actually need to do to balance it all out is I need to square this side as well. Okay, think about your locus. You had the locus between 2 points. Okay, we had to start off with the distance PA equals PB, all right? And then we can eliminate the square root because they're the same thing on both sides. So that's what I'm doing here, finding the distances from here to here, using the right-hand side, but to balance it all out, I should square the left-hand side. So 16 x squared plus 16 y squared. Okay, expand all that out. So x squared plus 4x plus 4 plus y squared plus 2y plus 1. Alright, so we keep going. So we've got 15 x squared minus 4x. Okay, now I'm going to leave gap because I need to complete the square so I can find the equation of the circle. 15y squared the 2y need to come over this side. Right, and just to make things a bit easier for myself, any constant numbers are going to stay on the right hand side. So 4 plus 1 is 5. Okay, so to complete the square, do you remember what we need to do? Yep, before I do that, for this example, what do I need to do first? That halving then squaring works only when this coefficient here is 1. Okay, so we actually need to factorise 15 out. So 15, x squared, take away 4 on 15x. Okay, now to complete the square, I'll halve it and then square it. So it'll be 2 over 15 squared. Okay, plus 15 y squared, take away 2 on 15 y. So halve 2 over 15, which becomes 1 over 15, and then square that. Okay, so what I've introduced on this side, I must also introduce on the right-hand side. It's going to be 5. So I need to introduce this 2 over 15 squared, but I'm also multiplying that by 15 because I've factored out that 15. Okay, so 15 lots of 2 over 15 squared and add our 1 over 15. Okay, because they both have a factor of 15 out front. Yep. Alright. So, 15. So we've got x plus 2 over 15 all squared. I've set it up so I can do this. Plus 15 y plus 1 on, sorry, we've got to watch the sign in the middle. This is minus because the middle terms are negative. Okay. So you'll try to make it a bit easier for me now. Do you want to just calculate that on the right hand side? Sorry?
1 over 3.
Oh, there's two different answers there, wasn't it? You sure?
The first one was 215.
Did you open brackets, big brackets there in front of the 15, done all that? Take your word for it.
It's only got a 10, isn't it?
Sorry?
It's only got a 10, isn't it?
It's going to be 5 plus 4 on 15 plus 1 on 15. Because this is squared. So you can cancel that with the square on the bottom. So 4 on 15 plus 1 on 15, that's 5 on 15, which is 1 over 3. What's 5 plus 1 over 3? Which is not 10, it's not a third. Okay.
15 over 3?
Hey. What are you doing in your calculator, Rob?
1 over 3.
Yeah, that's for the 15.
Oh, yeah, plus 5, hey.
Add 5. Okay, so both these have a factor of 15, so I'm going to divide on the other side by that. So that means my x take away 2 on 15 squared plus my y take away 1 on 15 squared is going to be 16 over 45. And look at that, 16 and 45 are two square numbers. Okay, which makes it a bit easier in terms of what I need to do. So, algebraic method, so this is equal, I haven't told you there. Alright, so, this is like your mathematics equation. Alright, so that's what we need to remember. Alright, so the centre is going to be at 2 over 15, 1 over 15, and the radius is going to be 4 over 5. Okay, so remember, this is in your mathematics, this is x take away h squared plus our y take away k squared is equal to r squared. Okay, so the centre, there's plenty of room for that one.
16 over 45.
Pardon?
Wait, no.
Yeah.
45 times the...
Hang on. Oh yeah, that's right.
It's not 49.
What am I doing? 16, root 16, 4, 45, 9 5, so 3 root 5. Okay, I think at this point I'll do an approximation. What was root 5? What are the two whole numbers root 5 lies between? From yesterday's lesson?
2
2 and
and 3.
3. Okay, so 4 over 3 times 3, 9. 4 over 6 is somewhere between 2/3 and 4/9. 0.6 will do. Okay, so centre was 2 over 15, 1 over 15 there, and the radius is going to be larger than the distance of that point, the modulus of that point from the origin. Okay, but when you do the circle, you need to show for that circle that if the radius is larger, so it's going to have intersection of both those values because 0.6 is going to be greater than 2 over 15 and also greater than 1 over 15. Okay, so some sort of representation that yes, it crosses at 4 point. Just label the centre and show that the radius cuts 4 places. Okay, if you need to determine the intercepts, you need to do algebraic rearranging and solving to find the values of the intercepts. Okay, so the x-intercept y equals 0 and the y-intercept x equals 0. Substitute into the formula we've just got at the end of the last page and find the values. Alright, but we won't worry about that right now. We'll just worry about making sure we can draw the locus of the circle in complex form of the formula from before. Right, question. Right, a couple more. So now we've got some arrays. So what's the definition of array? So what a line, an interval, and array. So what's the difference between them? Where do you, what topic do you see raising? Angles?
Oh, so it doesn't have a name.
Pardon?
Is it just not
A line does not have a starting point and does not have an end point. That's why we put the arrowheads on the start and the end when we graph linear relationship. Okay? An interval has a starting point and has an end point. Okay? Array has a starting point but does not have an end point. Okay? And that's how we form angles, because they have a vertex and then the line keeps going the other direction. Alright? So that's the definition of array, and there it is. It's also vector. The vector xy. Right? So vector is also array. Okay, so the argument will provide the rays. Okay, so when you see arguments, you're often going to be looking at rays. Okay, so the argument of z plus 2 take away 3i is equal to 3 pi on 4. Alright, so first things first, the argument of z is theta is a ray, the end at the origin, but it does not include the origin. Okay, I'll get to that in a moment. With an angle theta with the positive real axis. Okay, so just like we've been doing the calculating the argument. And the argument of z take away omega is equal to theta is a ray, which is the end point, or the starting point really. Start. At omega, but does not include omega, and has an angle theta with the positive horizontal line at omega. Okay. So again, this is another one of the z take away omega. So we need to find where omega is by appropriately swapping the signs around, because we need z take away omega. In other words, arg of z take away a negative 2 plus 3i is equal to 3 pi on 4. Okay, so what is the degrees for 3 pi on 4? Okay, so in other words, it's going to be in the second quadrant, halfway through. Okay, because it's pi on 4, which is 45, so you're going to have 45, 90, 135. Alright, centre at negative 2 plus 3i. So, negative 2 plus 3i. There's your omega. And the positive horizontal line at omega is where you start your argument. Okay, so that's the point there. However, I've actually done. Okay, it is actually an open circle to start. Why? An argument is measured from a ray, it's not measured from a point. Okay, so if you have a point, the argument of that specific point doesn't exist until you know the direction of the line. Okay, so that's why when you do your argument, it has to be an open circle. Okay, so 135, so we're going to go 3 pi on 4, or 135, off in this direction for the ray. Okay, and that's Locus C. Okay, only when I know the definition of the line, I can then define all the other points, but I cannot define that starting point. Okay, so again, 3. Okay, so at least make a marking of your centre point. Right, and the next example. So pi on 6 is less than the arg of z, which is less than pi on 3. So what do you think we're going to do here? What about that? What if it was argument z equals pi on 3? What would it be? Hey? Well, it just had an argument of z equals a number.
Will it be a fat ray?
Sorry?
Will it be a fat ray?
A fat ray. Why do you say a fat ray?
Because it's an area that's going that way.
Well, it would the area, the region, yeah, not the actual ray.
Yeah, so it's fat.
Fat ray.
Fat ray.
Alright. So what is the locus of the argument z equals pi on 3?
So it's going to be like
Yeah.
an angle.
Yeah. Alright, because argument is between pi on 6 and pi on 3. So what's pi on 6 again? 30. What's pi on 3? So, argument z, the centre is at the origin. Okay, so we do a ray off at pi on 6 for the argument and a ray of pi on 3 for the argument, and we're going to shade the region between them. Okay, so again, open circle, because the argument cannot be defined at a point, it has to be defined with a line or a ray. Okay, so just a general form of the direction. Oh, hang on, what have I done wrong? Yeah, because it's just less. Okay, so you've got to be careful with these things. Okay, so I've done mine accurately. You just need to represent it generally. Okay, so there's your two rays. Right, and the argument of z, the locus, the region, is between those two. Okay, so okay, so today, that's the last one. Yep. Alright, so today we've looked at what makes the locus, what makes the line, what makes a circle, and what makes a ray, depending on the condition of what you've got. So in your note, they're all summarised there. Next week, we've got 2 lessons. We're going to spend the first lesson next week on doing Locus question. Okay, so incorporating all this in there. And then will be a working lesson, the second lesson to finish off the topic. Okay, and we'll start conics in week 6. Right, any questions?